So we are going to go through the last of chapter 9 today. Welcome everybody. And this it's kind of a little bit of a shift into Bayesian statistics. And I'm not a Bayesian, but I will tell you a little bit about what I think is going on here. I don't necessarily feel that this is super well explained for the Bayesian Gaussian mixture models. So we'll probably jump to something else, but let me first start with what he says. And then when it gets confusing, I will go somewhere else. So the idea is that with a Gaussian model, we can also use the Bayesian Gaussian mixture class. The idea with this is that the clusters that are not necessary are downweighted to small numbers. But the problem with it is that you have to set the number of clusters of n components to a value that is greater than the optimal number of clusters. So the algorithm then goes and eliminates the unnecessary clusters automatically. So in this example, he is going to pop this over here. Okay. So in the example that he provides, he calls the Bayesian Gaussian mixture and imports it with 10 components and a n init of 10. He is giving us, he calls it fit it, and when it's called to fit, it's interesting. There is actually in my version at least, I'll show this. Oh, I'm sorry, I thought I was showing the screen. So let me go through this again. So we're going to look at the Bayesian Gaussian mixture class, and you have to set the number of components to more than the number of clusters that you think you're going to end up with. So I guess theoretically you could set it to a very high number and work down. We can see if that actually works or not. So with this code, he is setting the number of components to 10. So his guess is that it's going to be, the number of clusters is going to be somewhat less than 10. And if you remember from our time previously, it's like kind of like 3 or 4. And we set an n init of 10 for 10 different runs, and then we call the fit. And what's kind of interesting here is that I get a convergence warning. Kind of interesting. Not sure what that necessarily means because it seems that we get a reasonable result.
Yeah, I got the same thing when I try. The random init equals 42, whatever that was. I changed that random seed and then it it didn't have a problem. So I got the message that the 10th iteration didn't converge. Is that the same thing you got?
Initialization 10 did not converge. Try different initial parameters. Yeah, I got the same thing. So interesting. But if you got 9 convergences and 1 non-convergence, does it matter? I don't know.
I'm not sure.
So I mean, with all these things, it's kind of, with all this machine learning, there is a certain amount of art to it still, despite the auto ML people that would protest otherwise. And Bayesianism is certainly an art. So we'll go through that. So it detects there are only 3 clusters, gives a array. These are the probabilities. And we can plot them. We go 1, 2, 3. So I'm going to switch back to the book for a bit. And what he explains is that the parameters of the cluster, including the weights, means, and covariance matrix, are no longer fixed model parameters, but are latent model parameters. So Z includes other internal values as well as the label assignment. Now he starts going into some funky stuff, which I will dutifully discuss, but I don't necessarily know if this adds a great deal to the conversation without just being a lot of math that is kind of summarized too much to make sense. And I'm going to start this a little bit differently, okay? Because I would like to jump to page 272, and I would like to talk about Bayes' theorem. And I don't believe that Bayes' theorem was covered previously in the book. I kind of came into this a few weeks late. So if you did cover it, well, bully for you. But Bayesian statistics is an entirely different branch of statistics, as much as I can understand, but it's a competitor to the frequentist statistics that you and I typically use. And the important point of Bayes' theorem, and how I like to think about Bayes' theorem, is that it's a hunting algorithm, in the sense that you take an estimate, right? You look at it, you compare it to some data, and you say, well, how good was my guess compared to the data that I have? And then you adjust it. And in my mind, that sounds a lot like stochastic gradient descent, where, we take a look, we use our training data, okay? Now we run our validation data. We take a look at our validation data, and we say, are we doing good or are we doing worse? And if it says we're doing good, we kick it a little bit more towards this part of the gradient to descend. And if we're doing a little worse, we kick it the other way. So this is kind of the idea of Bayesian statistics and Bayes' theorem. And it basically deals with this PZ of X, okay, which is called the posterior probability. And the posterior probability, this reads the probability of Z, okay, as relative to X. And X is our data set, okay? Z is those latent variables, including the labels, all right? P is just a probability. And it's the posterior. Well, posterior, what the hell does that mean? Okay, sorry, heck. So what you need to think of posterior as is that it's posterior, it's behind, it comes next or after, okay? You have, in Bayesianism, your prior beliefs, and just make sure I'm sharing the right screen here. So you have your prior beliefs, and this is kind of where you start with this distribution, all right? Then you get some evidence, you get some data. You compare the evidence and your beliefs, and you say, well, this is not correct, okay? The truth must lie closer to this. So you don't just allow the evidence to dominate in and of itself, but you allow the evidence to inform your prior beliefs to create something that happens afterwards, or a posterior belief. And with Bayesian statistics, this is iterable, and you keep refining your approach. So, this is a nice little article on from Analytics, which is a nice site. I'm sure you all know it if you've been dealing with any of this. But the bottom line is, anytime you have a conditional probability, okay, you kind of have a Bayesian circumstance. So, in fact, there are a number of good proofs that came out fairly early in the deep learning data that showed that the deep learning algorithms were producing posteriors. So that's kind of fun to check out. So I'm going to go back to here for a second. And so this is our posterior, okay? Now we can kind of go back a little bit and not get completely skunked and confused with a large number of things he's going to throw out. So the first thing he's going to throw out, all right, is the internal variables. Okay, check. We understand that more is going on internally. We're comparing a lot more things. All right. The next thing he talks about is the beta distribution. And I have used, Gaussian distributions are fantastic, but there are other distributions as well, and there are quite a few. And, you may have heard of the gamma distribution, which I think is a fantastic distribution, really useful in healthcare, actually. It's kind of like a tail, almost like a one-tailed skew distribution. You have Poisson distributions, you have, a gazillion different distributions, but there is apparently this thing called a beta distribution. And a beta distribution is going to be a distribution that is controlled by two variables, alpha and beta. And the alpha and beta are going to shape the variable. And I believe that the beta is intimately related to the gamma in a way that I do not have the mathematical skill to even discuss, but it's there. So you can check this animation out. Look at all the different probability distributions that you can get from the beta distribution, which I think is super cool. So you're basically going from a Gaussian distribution.
Can you pause it on that one? The one that, pause it when it gets to where it's peaked at 1.
I don't think I can.
Oh, you can't pause it. Okay, well, maybe just watch for the one. Now, right there. That's the beta distributions that we're looking at when you take beta of 1 and alpha, where he calls alpha the concentration.
Right.
When alpha is equal to 1, then the beta distribution, beta of 1, 1 is flat. It's just a uniform distribution from 0 to 1. But when alpha is bigger than 1, is much bigger than 1. So basically, when alpha is near 1, the distribution is essentially close to being flat, uniform distribution, right? And that's what he talks about as a low concentration. And in other words, everything is sort of equally, the cluster, there are sort of equal number, the clusters are equal, the points are equally distributed among the clusters. Then when he talks about high alpha, that's when alpha is, let's say, 10 or something. So beta of 1 and 10, that distribution is the one that's peaked at 1, and then it sort of decays towards 0 as you approach 1. So let me see when it comes by, I'll tell you again. It's coming right there. Though that is the one where you have a high concentration. And so you can see what he means by high concentration. The probability is peaked towards the early clusters, the early the early part of the probability. Well, it's peaked towards the early part of the interval on 0, 1. And that means that the first few clusters are having lots of of points in them, and the rest of them are, in other words, most of the points are in the first few clusters, and then it sort of the probability sort of tapers off.
Yeah, I just think it's kind of cool that you go from like a Gaussian distribution there to a Poisson, and now you're actually starting to go to something that looks like this is a gamma. Now you've even gotten to a logarithmic distribution there. I mean, it's very interesting the different shapes that you can get with the beta. I've not really played around with it or considered it ever, but it seems like it's pretty versatile.
Yeah, especially, I mean, anything that's, the Gaussian distribution is on an infinite, is from minus infinity to infinity. But whenever you have something distributed on a finite interval, that's where the beta distribution is really, like you said, really versatile, because you can model almost any kind of shape. In fact, I think you can model any shape on that interval.
You probably can with that. So if you look at this picture, there's a whole just a mess of different functions there. Okay, so we talk about the beta distribution, and then he talks about stick breaking process, which is basically what he's basically doing is he's doing a train test split repeatedly with different values. It's like I'm going to take 30% of my test set or 30% of my whole set and reserve it. Then I'm going to put 60% of the remaining and reserve it, 50% of what's left after that, so you're just kind of, run train test split like multiple times and sequentially. So, all right. Joe talked about that already with the alpha values. And then he starts talking about the Weisart distribution to sample covariance matrices, blah, blah, blah. Okay, maybe. I don't know that, so I'm not even going to try there.
I would just comment that this is not a well-written part of the textbook.
No,
so
it's not a well-written part.
Yeah, it's he introduces terms without explaining them. So if you're lost, don't feel bad. This is not something, it's not you, it's him. So,
no, I know. I think that maybe he was a little lost too. So I mean, it's fine. It's just
Well, it's more like he knows it cold, and and so he just thinks that everybody else should know it too. So I think that's the problem.
Yeah, it's like just popping out it's obviously the Hamiltonian. I mean, you can just pop that on conversation at a dinner party sometime and see what people do. So here he starts getting into the meat that we just talked about with the Bayesian prior. Okay, and remember, the prior is what you think it is. The evidence is what you feed into it, and then the posterior is what you get out. So we think that probably there are less than 10 clusters, so we're going to run it with a maximum number of clusters of 10. Okay, but what's interesting is that the more data you have, the less the priors matter, because if you have a lot of data, it'll converge or hone in on the truth because of the subsequent iterations and adjustment. Where it does become an issue, okay, is with strong priors or strong beliefs and little data, okay, and that's where you can get a large amount of variance. So if you're using this Bayesian method with a small amount of data, your hyperparameters become obviously very important. So we talked about Bayes' theorem, and he talks about the problem with Bayesian analysis in that it's essentially unsolvable as is. That's what he means by intractable. But, oops, I'm not sharing the right screen. So, this is, you're not going to get an answer. But there are approximations that can be done. One of them is variational inference, which picks a family of distributions Q that involves Z, the latent variables, and a new hyperparameter, lambda, which could be more than one hyperparameter, which is going to make Q of Z a good approximation of the P of Z relative to X. That is achieved by finding the value of lambda that minimizes the KL divergence, the Kullbacher-Leibler divergence from Q of Z to P of Z, denoted this way. And he talks about the KL equation here in equation 9.4 and rewrites it as the evidence or the data that you know, okay, not your prior data, but the data that you obtained, okay, the log of the evidence, log P of X, okay, minus the evidence's lower bound, which is called the elbow. Since the log of the evidence does not depend upon the distribution Q, it's a constant. So by minimizing the Kullbacher-Leibler divergence, you just have to maximize the elbow. So
I guess what he probably, well, again, this is not well explained, but so he introduces this Kullbacher-Leibler divergence, and he should have probably said what it is. It's basically a measure of the difference between, it's a measure of how different two distributions are from each other. So you can imagine comparing a uniform distribution and a Gaussian distribution, and the KL divergence would be some big thing. If the KL divergence, sorry, if the two distributions are similar, then the KL divergence is going to be small. So what he's doing is he says, okay, we want to pick this Q in some way so that it's close to the thing that we don't know, which is P of Z condition on X. And to do this, we're going to minimize the Kullbacher-Leibler divergence between those two things, and pick the parameter lambda that does that. So it still doesn't explain exactly what's going on, but in your head, you should think minimizing Kullbacher-Leibler divergence is akin to finding distribution Q that is very close to the distribution P of Z given a condition on X that we're looking for.
Yeah, it's kind of funny. I was actually just writing about this the other day in this paper that I've been trucking around now for a while. But you know, the idea being is that if you have different conditional probabilities, okay, and that's what you have in this setting, how can you compare the two? And you compare the two with the Kullbacher-Leibler divergence. You know, obviously this is you want to minimize this. And if you think about the shot in Vidya, if you think about this shot in Vidya, where you have the priors, your new evidence, your new data, forming a new posterior, okay, you can see that as you give new evidence, right, presumptively it's going to be closer to this zone than this zone. You're going to kind of hone in, and your posterior is going to kind of shift to match it over iterations. And that's the, you know, that's the corrective part of Bayesianism. And the KL divergence really is a similar thing. And by, you know, minimizing that KL divergence, you get a distribution that's as close to the, you know, the sum of the distributions of the evidence, you know, after those shifts. So,
aren't you getting a difference? That divergence, isn't that two very different things? Isn't that like really subtracting apples from oranges?
with the KL divergence?
Yeah.
Explain to me how it's subtracting apples from oranges.
Two different
Are
types of
you saying
distribution.
are you saying in the setting of the Bayesian prior and posterior because I don't agree. I think when you're doing this in Bayesianism and you're iterating over this, you're absolutely subtracting the same stuff, and your measure is the KL divergence. So the KL divergence is going to give you an idea of how good, or how close you are to being die, I believe.
Yeah. Okay.
Okay.
Oh, okay.
So,
Mhm.
yeah, I was just trying to, say that, you're never going to get a perfect KL divergence, because there's an error term in there that just kind of doesn't go away because of persistent residual entropy. But that's probably out of scope, so let's leave that alone. Anyway, okay, so going back to this. So how do you maximize the elbow in order to minimize your KL divergence? So you can use this mean field in variational inference by picking a family of distributions QZ lambda and P and the prior, the P of Z, carefully to ensure that the equation simplifies to something that can be computed. The answer is, unfortunately, there's no general way to do this. And so it's kind of guesswork. Then a simpler approach is the black box stochastic variational inference model. And at each iteration, you take a few samples, and they are used to estimate the gradients of the elbow with respect to lambda. And then it's used in a gradient ascent step. So you're climbing out of the well instead of going down. So that allows you to actually use Bayesian inference with deep neural networks, apparently. And I haven't studied those yet, so I can't really comment about it. So he gives us a kind of cool example with the ellipsoidals, and I will switch now to the collab. You guys getting dizzy from all my switches? All right. So let's go back to the variational Bayesian Gaussian mixture. All right. And we have our plots. We have our decision boundaries. He has a BGM low and a BGM high variant. And the differences between the two are that the prior here is 0.01 and the prior here is 10,000. So one is way off to the left, one is way off to the right. Not sure what this NN means. And he maybe 73 components to make the array work. So he fits these, okay? Here are the weights for the low and weights for the high. And we plot them out. And so with the low weight, there are two well-defined clusters here. With the high weight, you get 3 clusters, and they're less well-defined and less well-behaved. He points out that apparently there are 4 centroids here, and the right plot only identifies 3 of them, okay? And that is on purpose because the weight of the cluster here, sorry, the top right cluster is lower than the lower right cluster. So the probability is higher that any point belongs to this than that. he gives another example, which is kind of cool, and I've done a little other stuff with it too. I'll show you. With the moons, he says, well, okay, we're going to try to give it something that doesn't work on it. So we use a Bayesian Gaussian mixture to fit the moons. We're using 10 components and an init of 10 with our normal random state. And we're going to fit it, and we're going to plot our figures. So we have our moons, and using 10 and 10, we have these kind of like sausagey appearing things that don't necessarily fit the data great. And then there are a bunch of decision boundaries suggesting that there are more clusters. And he's stating that we have 8 ellipsoidal clusters. And what happened to my stuff? Bummer. Did that not work? Oh, that's a bummer. For some reason, I thought I had. Guess it didn't save. I had done some variations of this with some different numbers. Oh, actually, no, it's later on. Sorry, I did a different fit. So this is basically Bayesianism. My gut feel is that it's one of these great techniques that is fantastic for writing research papers, but I'm not really aware of anybody who's using this stuff in like real world application. And Joe, maybe maybe someone who's doing this, more professionally can to say so. But I see papers on this, but I'm not clear that this is more than kind of like it's another tool to use, but it wouldn't be my first line tool.
Right. But I guess the advantage of the Bayesian approach is that it can estimate how wrong you might be. Like it can give you an uncertainty on your answer. So most the models that we've been dealing with give you answers. They'll say, okay, your cluster probabilities are 0.2, 0.3, and 0.5. 3 clusters, and the probabilities add up to 1. But with a Bayesian approach, you can not only get the probabilities, but you can get uncertainties on them, and so on. That's the advantage of the Bayesian approach. So whenever someone asks you to solve a problem, it's always more useful if you can not only come up with an answer, but also come up with an uncertainty on your answer.
I cheat. I just bootstrap confidence intervals.
Yeah, there are ways to do that without Bayesian estimation. True.
Yeah. Okay, I'm going to switch gears just briefly now, and I'm going to go back to something that we didn't have the time to do previously. Page 258. Guys, do you remember this? So we kind of mentioned that there were other clustering algorithms. In the collab, there are 2 other clustering algorithms that he discusses, spectral clustering and agglomerative clustering. And I'm going to go through spectral clustering first and likely only. So spectral clustering takes a similarity matrix between instances and reduces its dimensionality using k nearest neighbors, okay? And that's strange, 250. Okay, and sorry, it doesn't use k nearest neighbors, it uses k means in this low dimensional space. And it's supposed to be able to capture complex clusters and also reduce dimensions so that you can identify graphs, okay? But it doesn't scale well to large numbers of instances, and it apparently doesn't behave well with clusters of different sizes. So I'm going to switch to the Colab here. And here's the example on spectral clustering. So you import spectral clustering, you assign it to an object, spectral clustering 1, he gives us 2 clusters, a gamma of 100, and since it's a spectrum, I think I would think of gamma as like a temperature almost, okay, and a random state of 42. We can take another one, SC2, spectral cluster example 2, with a gamma of 1, okay, and for completeness' sake, I threw in, which is not in your Colab, spectral clustering 3 with a gamma of 50. So when you calculate the percentile of the affinity matrix at, I believe, the 95th percentile for SC1 with a gamma of 1, SC1 was a gamma of 100, it's 4.25%. For SC2 with a gamma of 1,000, or sorry, 100, it's 95, 97%. And for SC3 with a gamma of 50, it's 21%. So if we plot these out, here is gamma 100, where we separate the half moons, but you see there's quite a few clusters, but the decision boundaries are fairly taut. With a gamma of 1, the decision boundaries appear to kind of bleed into each other, and there's misclassification of this shared area of the moons. So when you look at 50, now you have correct classification, but the decision boundaries are larger. So I thought that was kind of cute. I looked at this agglomerative clustering example, and this appears to be like very incomplete to me. I don't think this doesn't really make sense to me, Joe. And
I looked at it too. I didn't make any sense out of it either.
So here's an article from the Geeks for Geeks site on agglomerative clustering with Sklearn, and they're using it on their own data set. And they first reduced the dimensionality of their data through PCA and normalize it and make dendrograms. And they say, okay, there are like 2 clusters here, according to them. So they use this agglomerative clustering on the data set in a visualization. These are the 2. These are 3 clusters, 4 clusters, so forth and so on. And they make a silhouette graph, and okay, we made pretty pictures, and we're going to determine the optimum number of clusters. 2 and 3 look about the same, and then it goes down, so probably 2. They're going to just take the highest score. So the optimal number of clusters for the given data is 2. Okay, so that's agglomerative clustering. I really don't have anything more to say about that. I will go back to here, to page 274, and just note the other algorithms for anomaly and novelty detection with a little bit of a little bit of love given for PCA, because it's such an awesome thing to do, and mention that also fast MCD in the elliptic envelope class can be used for outlier detection. The concept of an isolation forest, which is a random forest where you purposely chop all the trees down into as far as they can go and try to find out the anomalies, or rather the outliers, which is kind of a neat idea. And the local outlier factor, which is based on k nearest neighbors, and the outlier is off on its own. And this I thought was kind of cute, a one-class SVM where instead of trying to separate the instances in high dimensional space, you want to put all the instances into a dimensional space, and then if a new instance doesn't fall into it, it's considered an anomaly. I thought that was pretty cool. Anyway, there's a lot of difficult material in this chapter. I kind of wish that we were further along and we could have talked a little bit about unsupervised learning, rather semi-supervised learning, as it is related to deep learning applications, because I think that's more interesting. Maybe at some point we'll get a chance to talk about that in the future. But I think I am done here if there are no specific questions. And I thank you for your attention the last 4 weeks.